www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So today we'll talk about surface recombination and generation. This is lecture 15 of the series. Now, in the last class, we talked about bulk recombination, that if you have a piece of silicon sitting on your table and you put shine a flashlight on it, then we saw that excess electron holes are generated, and if you turn it off, then they recombine. And they have various channels of doing so. They can go through traps, and in that case, remember, they need a phonon to help them match their wavelength, because generally the bottom of the conduction and bottom of the valence band, bottom of the conduction and top of the valence band, they are not aligned. Phonon helps them, or the trap helps them to provide the extra momentum. OJ recombination, two bumping against each other, one going down and the other going up in energy and gradually relaxing down. All those channels essentially conspire together, contribute together so that the electron can come back to the equilibrium state. Now, that was for the bulk happening inside the semiconductor. Now, you know that most transistors are actually very, very thin, right? Very thin. And surface is a very important property. We'll see MOSFET transistors are primarily surface, where the electrons flow a slither below the surface. So surface is actually everything. And how electron and holes recombine on the surface, not in the bulk. Bulk was last class. How they recombine in the surface is an important property that we have to understand. So we will talk about nature of interface defects in the beginning. Then we will see how to adapt the formula that we have already done, adapt to interface charges, interfacial states, and how the recombination now can proceed through the interface. And we'll give you some example that how to use this formula, just like last class, right? The formula itself was very complex. It has a lot of terms, NP minus NI squared, a bunch of terms in the numerator, but under appropriate conditions, they simplify. And in that case, we can just get a quick feel about how the recombination will proceed based on a very simple formula. So that's something we'd like to do, especially under depletion region. Again, this depletion region is something that occurs in the MOSFET a lot, and that's why we are in anticipation of a future problem. We are solving it here. Here you may not see the context yet, but eventually you will see. Every problem I'm solving, every one of them will be used later on. So we are preparing ourselves for it, and then I'll conclude. Now, the problem I'm talking about today was one of the fundamental reasons why MOSFET transistors, which is in your computers, although it was sort of invented or proposed beforehand, patented beforehand, 1930s, but because of this reason alone, this type of interface traps region or interface defect region, it didn't really fly. The first one came around about bipolar transistor. That was the first one in 1947. That was what was invented and eventually came to the market ahead of time. But even for the bipolar transistor, there was a big problem. And the big problem is the following. And now, I'm not going to go through the details of this. I will show you this again at a later time. Only thing I want to show you here that this is three different regions. Let's say an emitter, the yellow region, the green is the base region, and the current, the red arrow is showing that current is supposed to flow from somewhere, one terminal to the other. Why they flow and under what conditions, we'll talk about that later on. But the problem was that you see there are lots of exposed surfaces. These exposed surfaces on the corner, electron can not only go through the bulk and recombine in the process, but they can also creep along the surface, and surface is exposed to the outside world. Do you remember in the early days, in the first or second class, we talked about not only about volume, that what happens, number of atoms per centimeter cube, how to compute that. But we also talked about in 100 surface, how many atoms do you have? In 110 surface, how many atoms do you have, right? You have done homework. This is in anticipation of this problem, because depending on the surface you will have different number of atoms, and in the process there can be recombination. And it was a big deal, a big problem. And that's why many people do not know that the original transistor that was invented in 1947, that never went to commercial production because of this problem. And the first person to solve it, really in a significant way or in a proper way, is by actually covering that region up, and I will show that again in a later time. Instead of keeping the side region exposed, actually covered that up, and then in the process make these transistors robust and manufacturable. And this is the right hand side. That is what made integrated circuit possible. If had it been things like on the left hand side, that would have been a disaster. No integrated circuit would have been possible. Bottom line, surface recombination is a very, very important thing. And you may not have heard about this person, Huarne, but this is one of the leading person. This is one of the 8 people who are sort of responsible for the initial stages of transistor development. Significant contributions. And so bottom line is that surface recombination is important, and we'll see it many, many times during the course. So again, just in another point of view, that you remember this particular picture, that it was silicon on the bottom, single crystalline silicon, and then there was an amorphous oxide, right? Do you remember? In the middle region, here I show 16 angstrom. These days, most of the transistors have about 12 angstrom of oxide. It's even thinner than a DNA. DNA, double-stranded DNA is 22 angstrom. And this is almost half the size of the DNA, and then polysilicon transistors. Now, if you look at the silicon, you remember that the silicon is tetrahedral structure, right? And we pushed it flat on the surface, and that is how we have drawn it. And the circles are each silicon atoms in the crystalline phase, and the double lines are essentially the lines of the covalent bonding between silicon, right? So you have 4 neighbors, tetrahedral structure, and you can see every atom on the planarized version of it still has 4 surfaces. Now, this of course continues up and down. Had it been a bulk, this would have continued up and down. But just think about the row just on the surface, Then what would happen? This is what is going to happen. Now, anytime you pull the silicon up, the silicon that was sort of terminating, providing an electron, participating in the double bonding, it will take its electron out. Now, if it takes its electrons out, then the remaining silicon on the surface now are in trouble, because they cannot no longer have the 4 electrons from the neighbors that was necessary to complete its bond. And so then each one of them is sort of deficient of 1 extra electron, right? Do you see that? And as a result, what will happen, by the way, these are called dangling bonds. Now, itself is not dangling. It is fine its own, but it is anticipating, waiting for another electron to come along. Now, you can see that if this was the case, if we didn't do anything to this problem, then this is what's going to happen. As if you think about 2 electrons, the fate of 2 electrons, then 1 electron could just go, no problem. So it can go from one part to another, travel, that's fine. But what would happen sometimes, once in a while, what would happen, that this electron would come in, and instead of going where it was supposed to go, it will find a local bond nearby. Remember, it's supposed to be a double bond. So it's very energetically favorable. It will just go and stop there. And if it goes and stops there and then comes back, it will be a very horrible, noisy transistor, because sometimes it goes, sometimes it doesn't. Moreover, if the charge is sitting there, sometimes it says, sometimes it doesn't. I'll show you later that something called a threshold, the electrostatic potential of the silicon underneath, would be fluctuating wildly. That's no good. And that's a big problem in transistors these days. So, in fact, a significant fraction of my research is based on what happens, reliability physics, what happens when bonds are broken in a random way. And this is one of those problems, a very significant problem actually. And this problem was eventually was solved in Fairchild in 1965 to 1967. That is when this problem was solved. Before that, no MOSFET was possible. MOSFET came along that time because after solving this surface passivation problem. Okay, so how does the surface states look like? So think about, so what I have done in that picture on the top with circles all around, I've rotated the previous picture from the previous slide 90 degrees. So you can see single bonds facing towards the right. Now think about the dark blue line. I have taken a cut and I'm looking at the potential, electronic potential going down. And in the bottom, what you see is this electronic potential going up and down. Do you remember chronic penny model? The chronic penny model was series of this, right? Going up and down, up and down. But the only difference here is that it has reached a surface. Now when it has reached a surface, you can see on the bottom, the dark blue one, the potential has gone up because it doesn't want electrons to go out. It is like having a table. Now electron or electronic wave function should not be able to jump out of the table. Otherwise the table would dissolve, right? So close to the surface, then there is a potential barrier. And as a result, what I'm showing here in the green is the electronic wave function. And you can see it's more or less periodic, but towards the edge, it's not periodic anymore. So when you solve Schrodinger equation for this problem, chronic penny equation for this problem, not only you will get normal bands, conduction, valence band and all those, but you will in addition get bands in which there will be extra levels. Now these are called surface states. Now this is very different from this trap levels, right? Trap levels were foreign atoms like gold, copper coming in silicon. So this was physically a different material that gave a different trap level. Here, no foreign material. It is just that I have terminated the barrier and therefore I have introduced a level which is solution of the original Schrodinger equation, but with a new boundary condition, you see. And as a result, what will happen is that we'll have an EK diagram, and this EK diagram, in addition, will have a level shown here in a blue level in between, right? And this is one of the surface levels, surface states. Now, that is the EK place. After solving the Schrodinger equation, you will have an EK diagram, and correspondingly in the real space close to the surface, the dark blue, do you see in the middle between conduction and valence band? That's the surface states. These are not foreign atoms. Anytime you cut a bulk material, you are going to introduce one of those states. Now, what is going to happen is through those levels, electron from the conduction band will be able to jump to the valence band through the help of these trap levels or surface state. Now, this is not a physical state in the sense of a trap level, but of course it functions as if it was one. So we have one at a given energy, and where is it? That depends on where the surface is terminated. That determines it. Now, assume that instead of cutting on the top, an electron is coming somewhere near the bottom. Again, 90 degrees, same way they rotated. Now, I have shown here something which might surprise you a little bit. On the left side, what you see is the electrons were sort of, silicon atoms were coming down, then it sort of got shifted, and then it coming down again. What is that all about? This is because anytime you have a surface, you cannot have absolutely plain surface. Not possible. Anytime you cut it or anytime you break it, what happens? It goes flat a little bit, and then an extra layer of atoms are gone. Sometimes an extra layer, 2 layers of atom are still there. So on the atomic level, there is modulation of the height, going up and down a little bit on the order of a few angstrom. And this is present anytime you try to terminate a surface, right? So on the bottom side, what I'm trying to show on the left-hand figure, what I'm trying to show is a consequence of the height modulation. And what will happen as a result? What will happen as a result? That the potential going from the left to the right will not be exactly the same. And as a result, you will have a corresponding for the red, you will have a defect state which will not be exactly in the same place as the blue one. It will be slightly different because of course the potential is slightly different. So when you solve the Schrodinger equation, the state is in a slightly different place. Okay. Now as a result, what will happen that there will be a corresponding electronic state, but see here, the red is slightly different position in the conduction band. You see that? And as a result, now again you will have another electron recombination path, but it will be through a different state. So what is happening here is that the surface is sort of non-smooth. Had it been an absolute smooth surface, only one defect or only one surface state. Because of this surface oscillation, there will be a series of them essentially populating the entire band gap. That's why surface states are so dangerous. You know, copper or gold gives you one level, sits in the middle, it helps a certain recombination, no problem. In the surface, there is a series of them throughout the whole thing. And therefore, lots of ways for the electrons to come down to the valence band and recombine. Recombination we don't want for the time being. There are devices where we want it, but for these, we do not want. And therefore, an entire series of levels, it will be full. Remember, each state is coming from the consequence of this thickness modulation or height modulation. Now, one thing, again, I have on the left-hand side, I have rotated the picture, again, back to 90 degrees, just for one thing I want to make sure that you understand that recombination can only involve a single level. You cannot jump. Look at the version I have written on the right called wrong, right? Do you see right red shown here in red? Wrong, in which, what is wrong? I am trying to show an electron as if it is jumping first to the red level, then to the blue level, and then to the valence band. Instead of making one intermediate stop, it is making two intermediate stops. That cannot happen. Why not? The reason is, you remember, although I have drawn this picture in this particular way for my convenience, where all the trap levels looks like they are in the same position, they are really not. Look at the picture on the left-hand side, because the blue state came from a region which was vertical blue cut on the left side. On the other hand, the red surface state came from a region which corresponds to the vertical red line on the right-hand side. These two states are far apart. They are not from the same place. Do you see that? And therefore, an electron cannot start going down to the conduction band, or sorry, to the valence band, and then all on a sudden jump 20 atoms farther to go to the another level and then go down. That's not possible. Because this is like one high rise, you start going down, and then you have to jump to a different high-rise building and then go to the ground floor. Impossible. So actually, double levels, double stops, triple stops, impossible. Always a single stop as we are going from the conduction band to the valence band. Is this clear? This is a very important point, because if you don't understand this, you will not understand the derivation I'm going to do in a second. But it's a very important point that physically you should make sure that you understand why this doesn't happen. So let's try to now use, because it's one trap level or one surface state in between conduction and valence band. As far as math is concerned, you know, what's the difference? Whatever we did for the bulk, we shall just use it for this problem. But in the bulk, we had one level. Here we have a bunch of levels. We'll sum them up, and then we'll go home. So let's start. Let's start reminding ourselves what the formula was for single level bulk trap last class. Do you remember this horrible looking formula? Np minus Ni squared. In equilibrium, N naught P naught is equal to Ni squared. No generation, no recombination in equilibrium. Means huge amount of generation and recombination, no net generation or no net recombination. You can see the trap level sitting there, NT, number of traps. You have more the number of traps you have is in the denominator, the way it is, more the recombination will be. Now, I will have to do a sum a little bit later. So let me do this, a trick here. So what I have done is I have flipped the NT up. That's the only thing I have done. Nothing else is done. I have flipped the NT up. Now for a single level, now I have NT is the number of traps per centimeter cube, right? 10 to the power 16 per centimeter cube. But remember that I have interface traps throughout that energy region. So instead of writing it at NT as a single number, which is integrated over energy, why not I write it as effective density of traps per unit energy, D sub T of E, certain number per centimeter cube per EV, right? Multiplied by EV, delta E, the small region I'm thinking about. So dimensionally, these two are exactly the same, but I'm talking about a certain energy E. That's it. I haven't done anything here. Right? Okay. Now, if I know that's the recombination for one surface state at energy E, what do I have to do in order to sum them all up? Just do an integral. Because I'll just integrate over all those energy levels of the single surface states. Why do not I have double integrals where electron comes down once at one level, makes another stop, and then goes down? Is because what I just explained in the last slide. You are not allowed two stops going down. So it's a simple single integral over energy of that original formula, and you are done. Okay, so let's think about a case in which it's a example case about how to evaluate that formula, and let's try to do that. This is a donor doped. Donor doped means primarily lots of electrons, right? Lots of electrons. Donor gives a lot of electron in. So we have a little bit excitation, let's say photogeneration I have, and as a result I have delta N S0. Why there is an S? Because we are talking about surface quantities. So in this addition of 0, I have a S sitting there, and I have shown light on it. There have been this extra delta N and extra delta P generated. I have turned off the light, and I'm seeing how the electrons are going down from the conduction to the Valence band. Do you remember the top formula? That's something you should remember, right? I have split the total concentration out into the equilibrium concentration and extra concentration, and delta N and delta P, of course, in general, can be the same. Now, essentially, you have we have done this in the last class, minority carrier injection, remember, in the bulk case. Only thing we have done N naught and N naught multiplied by P naught. What is it always equal to? Always equal to Ni squared. So you can see why I have gotten rid of that Ni squared. And also it's a minority ionization or minority injection, and as a result, the delta N multiplied by delta P, that term is gone, right? So I have just, you see, I have a delta P sitting on the top, and the trap levels, the effective density of traps at a given energy, those are in. Now, the numerator is something to think about. So let me take 1 second to explain it. First of all, you see, this time I'm not really immediately ignoring delta N and delta P, right? So first thing I am ignoring is that this is a donor doped material. Is that right? Donor doped means how many holes do you have? Let me give you an example. You'll understand how to think about this. What is Ni? 10 to the power 10 per centimeter cube. Ni squared, 10 to the power 20 per centimeter cube. Keep this number in your head. 10 to the power 20 per centimeter squared for silicon. Now let's say I have doped something with 10 to the power 18, right? If I dope something with 10 to the power 18, how many minority carriers I have? NP is Ni squared, N is 10 to the power 18, Ni squared is 10 to the power 20. I have 100. I have 100 of the other type of carrier. Is that right? So therefore think about it. 10 to the power 18, 10 to the power 2. Which one is bigger? So that is how I drop it. That PS naught term. That is why I drop it, because it's 100 compared to 10 to the power 18. Okay. Now, only other thing I have done in this expression is you will see I have pulled out the NS0 in that expression. There are 6 terms, so I have dropped that PS naught term, but I have kept that NIS and the PIS terms. This was the N1 and P1. Do you remember? What is the multiplication of N1 and P1? Always also equal to Ni squared. Do you remember from the last class? So I have actually just kept them, but other than that, everything has been pulled out. NS0 has also been pulled out. There is a reason why we are doing it in this particular way. And I'll show you in a second, because we'll have to evaluate an integral. I'm preparing the integrands in a way so that my life will become simpler. Now you can see that NS0 on the numerator and the denominator in the second line, that will cancel. So I have an expression that looks something like this. Now for next 3 or 4 slides, I'll focus on the denominator, because if I can do something with the denominator during the integral, I'm in a good shape. So we'll see. So this is the denominator. Looks horrible. Here's 3 terms. Well, 1 is not too bad. I have NIS divided by NS0. So that's what I have 1. And I also have P sub IS divided by N sub S0. What is N sub S0? Equal to the donor doping. This is a donor doped material. So that's why I'm carrying around those terms. Had it been accepted doped material, I would have to just do the other thing. Okay. Now, do you see the substitution I have made? NS0 in the extrinsic region. Remember that extrinsic region? Freeze out, extrinsic, intrinsic region. So I have replaced in the extrinsic region NS0 with N sub D. So that's a constant. Only thing I have to worry about now, everything I know now, somehow I have to take care of NIS and P sub IS. You know, this is just math. I'm helping you around. When you start reading through your textbook and going through the note, you will see this in 5 minutes. So don't worry about it if you are lost a little bit. Just look at the general concept, the tricks I make. Now, NS0, I can always write it as, for the second term in that last line, I can write it in terms of Ni, because this is something you have done before, right? EF minus EI, and beta is, what is beta? 1 over KT, 1 over KT. And similarly, the N1, N sub 1s, that one, you can correspondingly write an expression for this. Now, do you see that why these expressions could be correct? Because if you multiply N sub 1s with P sub 1s, again you see that it will become Ni squared. The magenta and the blue, if you multiply, do you see that it will become Ni squared? So essentially I'm writing down the expression just like I did it in the previous class. And when I cancel these terms, I get an expression which looks something like this, complicated, but this is the real form. Do you see E minus EF? E is the trap level now, right? Surface, one of the trap levels. EF, Fermi level. Fermi level I can find out. Where will I find the Fermi level from? Do you remember that we have solved N minus P plus ND plus minus NA? Remember that the whole thing set to equal to 0. That's where we found the Fermi level from. So let's say we find the Fermi level. Fermi level is known. E is whatever trap I'm talking about. So it is 1 plus Ex plus some constant, which is the ratio of the capture cross sections, and e to the power minus x. Do you see the minus sign in this one? E minus EF and EF minus E. So there's a minus sign. Well, I'm in good shape now. I'll be able to integrate this. So let's try to do that. In the top, I am showing one level. This is conduction and valence band in the blue curve. in the real space, electrons coming down from the conduction to the valence band. In the bottom curve, which is green, I'm plotting the denominator. You know the formula that I just derived, 1 plus Ex and plus E minus X. That one I'm drawing in the blue. X is energy and Y is the magnitude of the denominator. How does it look? I'm just looking at the function. So you have seen this. So let's try to evaluate that denominator at energy level E equals EI. Now when energy is E equals EI, at that from the previous expression, you can see that the second term will become Ni divided by Nd. Ni is 10 to the power 10, Nd is 10 to the power 18. So that number is gone. And the second term similarly is Ni over Nd. That term is also gone at the intrinsic level only. So the magnitude of the denominator at the intrinsic level is 1, essentially 1. So I have 1. You can see I have shown here in the red graph on the right hand side at the point where it is EI that the magnitude is 1. The denominator is 1. Now what happens in the denominator at E equals EF? Now if E equals EF, then from the previous slide you should put the expression E equals EF and the value for X, which is the difference between E and EF, that will become 0. So X is 0. So if you put X equals 0, then you will see that at that point the value of the function will be 2, right? And similarly you can get another point, EF prime, sort of on the other side, where the function becomes 2 as well. You know, you're plotting it. If you plot it in a computer, 1 second, it will give you a plot, right? In a calculator, if you do the function plot. So it will do you the function plot. And if you do that, you will see the function looks like this. Denominator is very small in the middle, but as you are going close to the surface or to the conduction and valence band, the denominator actually blows up, right? Now you see, I can now therefore approximate this in the following way. Because it is blowing up on the two sides at EF and EF prime, instead of carrying around the denominator and the whole integral, why not I approximate it with two functions? That is one function which is sort of infinity at the two ends and 1 in the middle. Now remember, these are the time when before a lot of computing power is available. This paper was written when? This was written almost in 1953-54. So therefore all these tricks and other things, these are historical things. Yeah, you may not really worry too much about it, but there is a very important point I want to make, which is something you need to know. And this one explains it. But let me first finish it. So essentially, I can replace the denominator with 1 in this range and with infinity outside. Now, do you see now why if a trap level is not in the middle, then it cannot participate in the recombination process? Do you see that? Because think about a donor level, which is very close to the conduction band. In the donor level, that one, the denominator is infinity. So surface recombination or any recombination will actually go to 0. Denominator is infinity, right? So therefore, a donor cannot be a recombination center. Had it been a recombination center, all electrons will immediately disappear through the donor levels. It's a very important point that you need to understand, that why, even when you have 10 to the power 18 number of donors or acceptors, why is it that none of them participate in the recombination process at all? That was a question last time, right? Somebody asked this question. I was trying to explain it in the board. Okay, so this is a approximation for the denominator. Now I am all set, because instead of doing all those integrals from EV, valence band to conduction band, and looking at the complicated integral, that's my integral. Why is it? Because the denominator is 1 But instead of going from EV to EC, conduction to valence band, do you see my limits now? EF and EF prime, because that is the only part where the denominator is 1. Outside, infinity. Well, if you put it infinity in the other one, that gives you 0 contribution, gone. And as a result, this one, if D of E, if I assume that it's more or less a constant throughout the gap, as it is shown here in a picture like this, on the left hand side, this is taken from the book. The left hand side is a valence band and the right hand side is a conduction band. This is plotting from various experiments, various references and experiments, the number of trap levels. Here shown how many, do you see? 10 to the power 10 per centimeter squared per EV. That's the typical unit, right? Effective defect levels. And it goes maybe go beyond 10 to the power 11 and 10 to the power 9. Yeah, let's assume for the time being that it's flat. And if I assume it's flat, if you want to put it in the computer and integrate properly, well, that's no rocket science either. But you can assume it's a constant. And then you are done. Then you see that all the traps between EF and EF prime multiplied by whatever is the average defect density, D sub IT. What is IT? Interface, defects at the interface or surface levels at the interface. And that's what you have. And the excess carrier concentration delta P is there. Why isn't there any delta N or any N? Because this is donor doped. Lots of electrons, just a few holes here. So therefore, you only see delta P. You don't see, it's not restricted by the number of availability of number of electrons, so you don't see any electrons here, right? And that whole term in the beginning is called a surface recombination velocity. By definition, the three terms C, the capture coefficient, C sub Ps, DIT, and EF minus EF prime, that together, you see, that's a material constant. Given a doping, given a certain doping, that's a constant. DIT is just a material parameter. Capture cross section is a material parameter. EF depends on the doping. But more or less, this S sub G is called a surface recombination velocity. It has a dimension of a velocity, and that is a number that you will see mentioned in many of the handbooks. And it's a very well-known number. People will say, oh, I have done a new processing, but my surface recombination velocity is horrible. They made a measurement. So let's say they will shine light and they'll see how the current is decaying. And from that, they will extract back the rate R on the left-hand side. And from that, they know what this delta P is. So they will extract back a surface recombination velocity. If it is horrible, that means they have to do something to the surface, because the surface is still not good enough for a good electronic devices. So bottom line is, somehow or other, suppress S sub G by improved processing, right? That's something one has to do. Now, just to give you one example, in terms of surface recombination in the depletion region, what is a depletion region? Depletion means it has been depleted of any carriers, means N is 0, S is 0, right? So that's something that's important. And how would things happen there? Well, that's what I have done here. Why am I doing this again? I have done all this complicated calculation and I just got a formula. Why am I doing this again? Is because, remember, in the very early part of the previous derivation, I assumed it's a minority carrier injection, right? Few carriers, donor doped. That's how I did the whole integration. If my original assumption is wrong, then I'll have to redo the calculation. But fortunately, it will not take as long. I'll have to start from the original one, but I should be able to drop N and P, right? Because depletion region. I have that, the same thing. And then I will be able to just rearrange the terms a little bit. And you can see that now this is a function. On the numerator, I have e to the power x. And in the denominator, I have e to the power 2x. Now, when you are in high school, do you remember this type of integral, e to the power x divided by e to the power 2x plus 1? Then you can make a substitution and get the integral. Do you remember what would be the answer? Tan, right? Tan theta. It will take a minute. I mean, high school had been a long time ago, right? Now, you can do this integral in 5 seconds. This will, you can pull everything out. Why have I pulled dit out? Uniform. I have assumed it uniform. I have pulled it out. Ni is, of course, I can pull it out. This little simple integral you can do in your slip. And then the answer is, by the way, just 1 second. So in order to do this integral, I need to take the limit to infinity, plus minus infinity, EC and EV to the plus minus infinity. I can do that because most important traps are always in the middle region, right? In the middle region. So conduction and valence band are many kT away, because 1 EV, even if it is like a 10 kT away, so that one for the exponential, it looks like infinity. So therefore, I substitute with plus minus infinity so that I can do the integral easily, and that's my integral. Do you see what the surface recombination velocity would be? It would be the geometric mean of this electron and hole capture, number of interface levels you have. Beta is 1 over kT, right? Pi over 2, that comes from the tan inverse when you integrate it between plus and minus infinity. Again, very simple formula, something that you can probably almost remember how to derive. Now, do you see a sign problem here? Not a problem, it's the right sign. What sign do I have? It's a negative sign. And why do I have a negative sign? Because when things are depleted, it wants to go back to the equilibrium. As a result, instead of recombining, it is actually generating so that it goes back to the equilibrium values. Therefore, I have a negative sign there. And compared to the previous case, we had a positive sign, right? Okay. Now, this is something I have already mentioned to you, that, and most students probably go out of probably finishing graduate school without realizing this, is that why the donors and acceptors don't act like a recombination center is because the place where the donors and acceptors are, the denominator at that level, at that point, E sub D, donor level, few kTs down, right, from the conduction band. At that place, the denominator actually blows up, becomes infinity, and therefore, no recombination generation through the trap level. And that's why you should always remember why they don't participate. The trap levels or interface levels, on the other hand, don't provide much electron as donors or acceptors. Those are very bad donors acceptors in the mid-gap region, but very good recombination centers. So both has the donors and acceptors has the same problem. Okay, so this is a quick summary of various types of recombination. For example, in depletion, what is something I just derived, the pi over 2, you remember the integration of tan inverse between plus and minus infinity. Minority carrier interface recombination derived in the beginning of the class, and compare them with the bulk minority recombination. Do you see dimensionally they are the same? Do you see that? Because n sub t in the third one for bulk minority, it is number per centimeter cube, right, per unit volume. On the other hand, dit multiplied by the energy. Dit is per unit energy, and that one, that multiplication energy range gives you energy. So together, this again gives you per centimeter squared or per centimeter cube. So dimensionally, they are exactly the same. A slight difference here and there, but exactly the same. Okay, so looks like that this is where we should end. Now, let me quickly point out a few things. So we'll go on, move on, and then attach contact to the transistor, and then we'll see how the current flows. This is all about recombination and generation. What is very important that this is sort of a detour in terms of we want to know how the current flow. It's a detour. But these steps are very important because when a device is good, somebody like you have a silicon processor if you join Intel today, and they know how to passivate the surface, how to reduce DIT to a value of, let's say, 5 times 10 to the 9, very little value, no problem. So if the process is already done, you really don't have to worry about it, almost negligible. But when you are a researcher or a new scientist working on a new material, in that case, you will ask a technician to go and measure you some data. You will set up, a surface. Remember this various orientations we talked about. So you will ask them, go and make this measurement and come back to me. Then you will have to deduce from that, what was the surface recombination velocity? Under what condition and how many do I have? And if you have too many, you will have to count the number of states on the surface and see what type of processing you can do to suppress the level. So when things are mature, you don't need to know anything. Others have already done the dirty work for you. But as a new scientist, as a new engineer, in that working on new materials, then it becomes central that you understand this and solve and debug this problem. You see? So that's why, although it's a little complicated math, please take a few moments so that you can understand them exactly, clearly, step by step, and you can apply it to a new situation, right? Okay, thank you.